Cleared up. Great. I'm Gary Hines. I'm also a Rio Brazos Master Naturalist, and I've known Brad for probably 8-10 years now.
Easily.
He's been helping us with our star parties for a long time now, and actually he's probably done hundreds, if not thousands, of star parties. A lot of them up in Badlands National Park, where he was the resident astronomer for at least 6 seasons. And all told, has probably approaching 6,000 hours of volunteer time in the national park system. So we rely on him for a lot of guidance, and we really appreciate his knowledge. And he is an amazing educator. And I think you're going to really enjoy his lecture today. He's a former Air Force colonel. He was a chaplain in the Air Force. But that doesn't mean he didn't get to go flying. He did go flying a lot and enjoyed it. Who wouldn't enjoy flying in the back of a F-14?
No. 15.
Yeah. And he's also jumped out of some, as we in the Army call, perfectly good airplanes. He's had several jumps out. But anyway, he's just a fascinating man, and I could really appreciate him. And I think you're going to appreciate him too. So let's welcome Brad Riza.
Thanks, Gary. Right off the top, you want to turn these off? Right off the top, I need to say a couple of things to you. Number one, I am not a university trained astronomer. I have 2 advanced degrees, one in theology and one in marriage and family therapy. So if your marriage is in trouble, I can help you. If you need spiritual counseling, I can help you. But I do have an ancient and revered degree. Great people like Abraham Lincoln had one. I have an SOMO in astrophysics, and I see some disbelieving faces. But that simply means I studied on my own. Abraham Lincoln studied on his own for the law and did pretty well for himself. So I've been a student of astronomy for a number of years, and I'll tell you the beginning of that story in just a minute. But just want to make it clear that I'm not a PhD trained astronomer, but I love what I do. And I hope you'll be able to see that in the next few minutes. I have been an astronomer in the national park system, which is kind of a fluke. Several years ago, I saw an ad in a magazine. My wife and I had just joined a group called Work Campers, WORKAMPERS, a company that finds short-term employment for RV owners and puts them to work in short-term jobs that they don't have to pay benefits and all those kind of things. So I saw an ad in this magazine for a new national park that was starting up. It was Minuteman Missile National Historic Site. Well, I was an Air Force officer, and I was assigned to missiles. And one assignment, I was not a missileer. I was not one of those guys who were trained to turn the keys and launch the missiles, but I did know that the pointy end went up. And so I called and I said, I'm just retired for about the 4th time. So I'm wondering if I could come and be a tour guide, a docent at Minuteman Missile National Historic Site. And the lady that I happened to talk to was named Allison Shoup, and Allison, park ranger, said, "Oh, when can you get here?" And I said, "Well, it'll take me, a couple of weeks." And she said, "The sooner the better." So we started making preparations to go to South Dakota, where Minuteman Missile National Historic Site is spread out in 3 different sites along Interstate 90. There's a visitor center, and then there's a real missile launch control center with an underground capsule where the crews used to sit, waiting for doomsday. And then about 10 miles on down the road, there was an actual missile silo that the Air Force gave to the National Park Service. And I'm thinking, this is going to be fun. So we're actually on the way to South Dakota, and my phone rings. And it's Allison. And she said, hey, Brad, about this job. And I went, oh, man, she's backing out. And I'm already a third of the way up there. And she said, I just read your resume online. And I said, I don't think so. I don't think I have a resume online. And she said, you ought to Google yourself. I suggest you do that occasionally. I found 2 resumes online. And she said, it says in your resume that you're traveling your travel trailer with a telescope. And I said, yeah, it's a hobby. And she said, well, your trailer is going to be parked in Badlands because we don't have a place for you to park at Minuteman. So you'll be living at Badlands and working at Minuteman. So I have a proposition to you. So she said, would you be interested in working maybe 3 days a week as a tour guide for Minuteman, and then maybe working 3 or 4 nights a week doing astronomy in the Badlands? And I said, oh, throw me in that bar pit. And so I did that for 7 seasons. We'd go up in mid-May. We'd stay till mid-September. And in 1 year, while we were still in South Dakota, I get a call from the superintendent at Big Bend National Park, and he said, hey, Brad, I know some stuff about you. And I said, yeah, I'm afraid that's out there. And he said, well, I've been talking to 2 of your supervisors there in South Dakota, and I want you to come to Big Bend and train some of my astronomers, some of my park rangers how to do astronomy. And so that year we left Granbury in May, went to South Dakota, stayed till September, came home, changed the stuff in the drawers in the travel trailer, hit the road for Big Bend, and we stayed there for almost 3 months. So I have found a love for the national park, and I found a love for astronomy. So I want to share a little bit about that with you, but let me tell you how this got started, because this is a really unlikely story. We have 2 sons. One of my sons and one of my grandsons is here with us today, but my other son, his name is Brandon. Brandon was not made for traditional school. We found out later, we believe that Brandon is a kinesthetic learner. If you're into education, you probably know what that means. But Brandon, some students can see things on the board. They can hear a teacher say things and they got it. Brandon, it couldn't make that connection. But put something in Brandon's hands and he had it. We didn't know that at the time, so Brandon was failing a couple of classes, and his overachieving mom and I, we did everything but beat him to try to get better grades, and I considered that. But as a marriage and family therapist, I knew that would get you a free trip to jail. So finally I said to Joy, my wife, I said, this is bothering us more than it's bothering Brandon. So how about we just tell him we're done griping about his grades? I mean, the world needs people to pick up the trash and people to dig the ditches. And so that's what I said to Brandon. If that's what you want to do, then please just do it well. And I'm not gonna rag on you about grades ever again, I promise. And he kind of went. But secretly, his mom and I said, anything this kid shows an interest in, we need to support. So less than a month later, he comes in and said, Dad, I want you to buy me this telescope. Well, I didn't know anything about telescopes at the time. I went out and bought what I thought was an expensive telescope. I have bought telescopes that are expensive, but I spent about $600 on this telescope, and he was happy as a clam. And then a couple of weeks later, he comes in and he says, "Dad, I need this astronomy book. It's about this thick, and it cost about $300." And I swallowed real hard and bought him the book. And so we're living in upstate New York. We're living in Rome, New York, right in the geographical center of the state. Brandon is outside with his telescope. It is March. There's still this much snow piled up beside our driveway. And Brandon is out there with the telescope. And I hear the front door open. Joy and I are all toasty warm inside. And the door opens and Brandon comes in and he said, Dad, come out. I'm looking at Eclipse of the Moon. And the door slams and he's gone. And I said to Joy, I don't want to go out there. It's cold. And she said, remember, we promised to support. And I said, then why am I the only one who's putting my coat on? But I walked out the door and I see the telescope over here on the driveway, and it's pointed up in like this direction. And out of the corner of my eye through the trees, I see the moon, full moon coming up over here. And I said something like, kid's into me for nearly $1,000 and he can't even find the bloody moon. And I probably said something about that caustic to Brandon, and he said, Dad, you weren't listening. I didn't say I was looking at the eclipse of our moon. I said I was looking at the eclipse of a moon. Okay, that's interesting. And he said, I am watching the eclipse of Io on Jupiter. And I said, well, dang, I want to see that. So Brandon and I stood out in the cold for about an hour and watched Ganymede pass in front of Jupiter's moon Io. And I was transfixed. I mean, I've had hooks in a bass mouth that weren't as hard as that hook was in my mouth. And I've been into astronomy ever since. And I frequently tell Brandon, thank you. When we retired and we moved here to Granbury, we built a house on Peak Road. And Brandon gave us an 8-inch Meade telescope as a housewarming present. And so Brandon and I have been connected by the stars ever since. The rest of the story, by the way, Brandon went off to the Art Institute of Dallas, and when they put paintbrushes and repeatographs and computer keyboards in his hands, the guy shot to the front of the class. And now he's out in California. For a long time, he worked for Blur Studio. He was a shot director and a computer animator, special effects guy. He and 3 of his buds have now created a travel app called Brink Traveler, and he makes more money than I ever thought about making. So if you have one of those kids, don't give up. Just pay attention to what they want and try to support that. So I'm into astronomy because of Brandon. So let's talk a little bit about solar eclipses. So tomorrow, most of the United States, most of the continental United States will see an eclipse. We won't all see the same kind of eclipse, but that's part of what we want to talk about. So that blue line down, across the United States, that's the line of totality tomorrow. So you're here partly because you want to see that. I'm here partly because I want to see that. And we're doing rain dances in reverse, trying to make sure that the clouds stay away. But as this chart shows you, even in southern Florida, they're going to see a 50% partial eclipse. Even up in Washington State, they're going to see 20 or 30% partial eclipse. The problem is with a 20 or 30%, it just kind of gets, kind of gray, but it doesn't get dark. And so if you're working, you won't even notice that. So that's why you're here, and we appreciate that that's why you're here. So let's talk just a little bit about what that means. So there are three kinds of solar eclipses. Total eclipse, where the moon completely covers the face of the sun. And then there's a partial eclipse where the moon is off center, if you will, and kind of slides along the limb of the sun and only shows, a partial eclipse. And then there's an annular eclipse where the moon isn't large enough to cover the entire face of the sun. And we see that classic ring of fire. And so when I say the moon is off center, there's some of you, you're not saying it, but you're thinking, how does that happen? How is the moon off center? And when I say the moon isn't large enough, some of you are saying, wait a minute, is our moon getting smaller? You have an annular eclipse? We're going to talk about that in a minute. But to understand some of that, we need to talk a little bit about some simple orbital physics. I promise it won't be painful. So this is the geometry of a total solar eclipse. Now this is way out of scale. So it is something like 400 times farther to the sun than it is to the moon. Well, you got to get that in your head first. 400 times farther. So back in the day, the heady days of NASA during the Apollo program, when we were actually sending people to the moon, it took 3 to 4 days to get a spacecraft from its launch in Florida to orbit of the moon. It would take about 1,000 days at the same speed to get to the sun. So those things, when you're watching Star Trek on television, and you see the Enterprise launch from Space Dock, at McKinley Station over planet Earth, and the next thing you know, boom, they're passing the moon. The next thing you know, they're passing the sun. Makes good television, makes really bad science. So it is a long way from here to there. I said it'd take 1,000 days. That's probably not true, because every second as you start toward the sun's gravity accelerates you faster and faster and faster. And by the time you get out here, I'm telling you, you're going to need more than the Enterprise's engines to keep from being sucked right into the sun. So don't want to go there. But what we're interested in is really right here. So during a total eclipse, there's a cone shadow that forms the diameter of the moon at the moon, and then it tapers down, depending on exactly what, it tapers down to a few miles wide on the ground. And if you happen to be in that few miles wide that strip showed you a while ago, you're in a total eclipse. So if you are standing right there, then you see a total eclipse. This area is called the umbra. I try to think of that as like umbrella. So it's the umbra that you're in that cone around the shadow of the moon. And then this other area, so what happens is this side of the sun's rays pass this side of the moon and go out here a ways in the earth. And so there's a shadow out here, but it looks like that. Right there in the middle, it looks like that. That makes sense to everybody? Make your head go this way. All right, so we're gonna move on. So this is what happens in an annular eclipse. In an annular eclipse, the moon is slightly farther out, and we'll talk about the why of that in a minute. But the umbra comes to focus before the cone gets to the earth. And when that happens, then right in the center, you see the dark side of the moon, and you see the ring of fire around it. If you're outside the umbra or the antumbra, in that case, right, in an annular eclipse, if you're out here, you're still in the penumbra, and you still see the same kind of solar eclipse. You don't get to see the ring or any of that magic that happens with an annular eclipse. Does that make sense? Okay, so this is what an annular eclipse looks like from first contact, a little more, until you get to this image right here. And that's awesome. I mean, that is amazing to see. So you have the shadow, you have the silhouette, not the shadow, you have the silhouette of the moon against the bright sun, and you can see the sun all the way around. But in a annular eclipse, you don't get to see some of the detail that you'll see in a total eclipse. And we'll talk a little bit about that in a minute. But that's what that looks like. So this is a really cool image. I wish I could say I took that. If I had taken that, I would have been aboard the International Space Station, which I would love. Yeah, but they're not going to let me fly, I guarantee you. So here's the dark side of the moon, and here is what we call Bailey's beads. So the mountains of the moon on the limb, as they almost cover the surface of the sun. Some of the sun's rays come through the valleys of the moon, and you see these lights like that, those sparkling around the edge. And so you can't see the cone of the umbra, but right here is where the eclipse is total. And as you move farther and farther away from that centerpiece, it gets lighter and lighter and lighter, and you're seeing less and less and less and less of the eclipse. So you really want to be right there.
What's that object in the back?
Well, the really cool thing is that during a total eclipse, you can actually see deep sky objects. So during the 2017 eclipse, I was in Alliance, Nebraska, and we were right in the path of totality. We were kind of up on a hill, and we saw the shadow of the moon coming. It was eerie to see this black spot on the surface of the earth racing toward us. And then just as the shadow came to us was first contact. And then when the shadow enveloped us completely, we were seeing the total eclipse. And all of this, I'm running 3 cameras because I'm thinking it's the only eclipse I will ever see. And so I've got 3 cameras going, and so I'm clicking. I'm not really looking. I'm thinking I'll look at these pictures later. And then my brain said, no, you got to look at this. And so I stopped for a minute and I looked up, and here's Orion. Orion is a winter constellation. And we're in August. And I'm seeing it in the sky because the sky gets actually that dark. I'll show you a picture that we hope, Brad's fingers across, that we hope it's gonna look like tomorrow, but we'll see. So we need to talk a little bit about phases of the moon. So a combination of Earth's gravity and the moon's gravity have conspired to make the moon tidally locked, is the astronomical phrase, with the Earth. So the Earth, the moon rotates around the Earth, obviously, orbits around the Earth, but it also rotates as it comes around. And see if I can show that to you. Gary, come up here, man. See, we got to find a place, we got room. So I'm gonna get Gary to stand here, hold my hands, and I want you to walk around me. So I'm gonna stop right here. That's about where we started. I want you to understand, you have seen a phenomenon that I did not see. You understand that? All right? Yeah, I'm seeing only Gary's front. So the whole time, you know, Gary was tidally locked, hand locked, with me as he went around me. So I only saw his front, but you saw him from every side.
Yeah, I did a full rotation.
Yeah, so you'll agree that I rotated once, right? You also have to agree that Gary rotated once. But his orbital rate and his rotational rate are the same. Everybody got that? That's a hard concept for some people to understand, but the moon always thinks. The moon we always see the same side of the moon. And we see the dark side occasionally, we see the lighted side occasionally, we never see the far side. And we didn't even know what the far side looked like until we sent probes, the Russians sent probes and orbited and photographed the backside of the moon. We have never seen, and you and I will never see anything but this side of the moon. So over at the Thompson Observatory, where I volunteer sometime, one of the guys built this, and he said, you know, this is easy we use this with kids. So this is the sun, and the sun shines on, you want to turn that on for a second? So here's the sun, and all of these little balls represent the moon in various phases. So if you put this over your head, then your head is the Earth. And so right now, you can see the lighted side of the moon, but I can't. So this is a new moon to me. And then here's a waxing crescent to me. First quarter to me. Waxing gibbous. Full moon. Waning gibbous. Last quarter moon. And waning crescent. And then back to noon. Kids get that right away. You get that? You're welcome to come out and try it after we finish. But it's really fun to see kids, and they say, "Oh, now I understand why the moon looks different." So we're tidally locked, and again, to be technical, the moon's orbital period is equal to the moon's rotational rate. And as the moon orbits, it's illuminated, as we've just seen, in different parts. So we never see the far side of the moon, but don't let me hear you say we don't see the dark side of the moon. Because I just showed you the dark side of the moon. So not only can we see it, we can take pictures of it. And I'll show you even a better picture in just a little bit. So here's another representation of this, except this is really bad. I've downloaded this from the internet, and stuck it in my PowerPoint. And then after I'd done that, I went, holy cow, that is really a mistake. Do you see the mistake? What's the mistake? What here's,
The sunshine.
yeah, the sun's shining on the moon and it's not lit up over there on that side. It's lit up here, and here, and here, and here. But anyway, it gives you a bit of an illustration, but it's not as good as the one that we use with the kids. So, so let's, so if everything is perfectly square, then why don't we have a solar eclipse every new moon and a lunar eclipse every full moon? Because we're not perfectly square. It is, I won't say it's out of whack, but as Kepler taught us back in the 15 and 1600s, orbits are not round, they're not circular. They're elliptical. And yes, I know, if you're a mathematician, I know that a circle is a special form of ellipse. But for our purposes here, I'm simply saying that the orbit around, the moon's orbit around the Earth is not perfectly the same all the way around. It is an ellipse. And so sometimes the moon appears to be farther away from us than it does in other times. You know, it's easy for you to see that if you put a quarter up in front of your face. I mean, it looks big if you hold it here, and it looks smaller when it's out there. Of course, the quarter's not getting smaller. Its apparent size is getting smaller. And so astronomers are always talking about the apparent size of X, Y, and Z. So the apparent size of the moon changes. So if you see the moon, you know, and when it's in one part of its ellipse, it'll look smaller. When the moon is closer, it's sometimes called a supermoon when it's really close to us and it's a full moon. So that's what that means. You hear the term supermoon, it's used too much probably, but that means when the moon is closer to us in a full moon, it just looks huge. And the other issue is that the moon's orbit around the Earth is tilted about 5 degrees. So this is what it looks like. Again, please, way out of scale. I didn't have enough room to, spread that out. But this is what's really cool. The blue line is our orbit around the sun. And then the red line is the moon's orbit around us. So you can see that, if the moon is, this many degrees, then over here, then it's going to be above our view of the sun as it becomes a new moon. Or if it's on this side, it's going to be lower. So it's going to pass below the sun at the new moon, and we won't have an eclipse. Eclipses only happen when this orbit of the moon, this is a node, by the way. So this line here and this line here pass right through there. And when that happens, we get eclipses. And if we're not looking at the moon in one of its nodes, then we don't. Then we just get a full moon or we get a new moon. But the figures in here are interesting. And there's a piece of this that you may not be aware of. I had never been aware of that until I started reading some things about astronomy, but it is 384,000 kilometers from the Earth to the moon, about 230,000 miles, roughly 250,000 miles. So, and this is the radius of the Earth, but You know what this word means? Who knows what barycenter means? Oh, good. I get to tell you something new. You're going to learn something new today, whether you wanted to or not. So the barycenter is the center of mass of this rotating combination. So have you ever seen, if you ever watched ice skating in the Olympics, and the guy's holding his partner hand and foot and swinging her around, you know, and he's not moving, just pivoting around, but he's leaning back. Why is he doing that? To counter effect the weight that he's swinging around. So even though the moon and the earth are not connected physically like Gary and I were as we were turning a while ago, we are definitely connected gravitationally. And so when the moon swings around the earth, it actually pulls the earth slightly, and we actually rotate around this barycenter, which is about right here. So the barycenter is 1,700 kilometers below the surface of the earth. So we orbit around like the ice skater, off center, but perfectly balanced. Does that make sense to you? So I just think that is crazy cool. So this is another drawing, the same thing. In this drawing, the sizes of the moon and the earth are to scale. So our moon is that percentage of size of our earth. But again, the distance between them obviously is out of whack. So we've talked a little bit about all this orbital physics stuff. So, so what does all this complexity give us when we're just in the right spot? No clouds. On just the right day, when all angles and orbits come together to make this magical moment of a total eclipse, what do we see? Well, let me show you. So here's the Intrepid eclipse chaser set up in Alliance, Nebraska. That is one of the imaging systems that I had set up that day. And so this is my first picture. This is just after first contact. This is the silhouette of the moon, and it's taking a little bite out of the sun. I have to tell you this funny story because after the 2017 eclipse, I read this article. A friend sent me this article and said, "Isn't this the most amazing thing you ever read?" And it was the most amazing. It was also the most stupid. So the article said, did you notice the sunspots that were all lined up on the surface of the sun? And did you notice that that's exactly the direction the moon went across? And so even the sun responded to this beautiful total eclipse by lining up its sunspots in perfect alignment with the path of the moon. And I thought, what idiot wrote this? The article was pulled from that paper really quickly. And I didn't write to the editor, but a lot of people did. So I'm telling you, our Earth and our moon have very little effect. We do orbit around a barycenter with the sun, but it is really, really, really close to the center of the sun. Because the sun, I don't know if anybody ever told you this, but the sun makes up more than 98.8% of the mass of the entire solar system. We'll let that sink in. That's one of those numbers that makes my brain hurt. the sun makes up almost 99% of the total mass of the whole solar system, including asteroids, including most of the comets, and even including Pluto. So we have very little effect on the surface of the sun. So this is the other second observing system that I had set up. I have a hydrogen alpha telescope that views sunlight only way up near infrared, and so it blocks almost all of the visible light and only lets you see this very thin line of red light. And so this is called hydrogen alpha. I was taking pictures with that, and then I was also taking pictures with my Pentax camera. And you say, wait a minute, Brad, a while ago the moon was coming from down here, now it's coming from up here. What's up with that? Well, if you know much about optics, every time you use a mirror, the image flips. And so my Pentax camera has one extra mirror that my telescope didn't have. So I'm getting these opposite images. So just so you know. So then a little bit later in the eclipse, you'll clearly see the sunspots that are aligning themselves to the path of the moon. And then much later, and then one of my favorite images just before the diamond ring effect. And then the diamond ring. So what happens here, just before the sun is completely covered by the moon, you get this burst of light that comes right from the very limb of the sun, past the very limb of the moon. And even here, you still need to have your eye protection on. And then we get to this. When it's a total eclipse and you can see the corona around the sun, you can safely take your dark glasses off, and it's safe to look at that. It's safe to photograph that without a filter. And the longer you expose that image, come on, computer, there we go, the better view of the corona that you get, until you get this one. This is my favorite one. I love this picture because not only does this show this is a solar prominence, this is actually solar matter that's being shot out into space, but all of this is photo energy that's being shot out from the moon, from the sun rather, and it follows the magnetic flux lines around the sun, and so you get these amazing patterns like down here, and how they cross right here, and how they seem to swirl right there, all magnetically. I mean, the sun's magnetic field is huge. And so it bends light. So I just love that picture. It's just one of my favorites. The other thing that I love about this picture is that you can actually see some detail on the dark side of the moon. How does that happen? Well, most of the Earth is not experiencing an eclipse, certainly not a total eclipse. And so most of the Earth is still receiving photons from the sun, and a lot of that energy bounces off our atmosphere, goes back into space, and in this case, lights up the dark side of the moon with what we call Earthshine. It's really sunshine, but it's reflected off the Earth, and so it's renamed Earthshine. And it just, I can look at that kind of picture all day long. So another funny picture, during the eclipse of 2017, my phone rang right in the middle of the eclipse, and I looked at it. I said, I'm not answering this. I'm busy taking pictures. I'm busy looking at stuff. So I called my friend back after the eclipse had passed us, and he was imaging. He was watching the eclipse from somewhere in Pacific Northwest. I can't remember, Washington or Oregon. But anyway, he called me and he said, Brad, did you see it? And I said, yeah, it was awesome. I got pictures and everything. I must have taken 200 pictures in 4 minutes that we were in total darkness. And he said, I mean, did you see the International Space Station? And I said, what? He said, the International Space Station went right across the sun. And he said, I said, no, I didn't see that. He said, how could you miss it? And he sent me this picture and he said, you know, it's right there. How could you miss that? So we're still talking on the phone. I hadn't seen his picture yet. And I said, well, Andy, the eclipse started out in the Northern Pacific. It crossed across, came into the United States, went all the way across and exited through Georgia out into the Atlantic. He said, yeah. And I said, but the International Space Station just crossed where you were. It didn't cross everywhere. And the phone was very quiet for a couple of minutes. I mean, well, not, surely not, maybe 10 or 15 seconds. And then finally he said, dang, I feel so stupid. Click. And he hung up, but he did give me the picture. And so I emailed him back and I said, yeah, great shot. I wish I'd been there to see that. But thank you for the image. And so I looked on the internet and I found a guy named Simon Tang was actually doing video that day. And this is Simon Tang's 27 frames out of Simon Tang's video that shows, you know, the transit. How cool is that? The transit of the International Space Station across the face of the sun. And so we have, because that happened, we had this picture that I showed you earlier. That the International Space Station was, you know, passing right in front of the sun during the eclipse, saw this umbra, this penumbra, and could see, you know, night sky things, deep sky things during the daytime. That to me is just absolutely awesome. So one more picture. This is what we hope. It's what we hope you might be able to see tomorrow. This is the eclipse sun, obviously. This is the planet Jupiter. And this is comet 12P Pons Brooks. I've imaged Pons Brooks right after sunset a few nights ago. Took a picture, not that good. This is off a planetary program, you know, like Starry Night and some of those kinds of programs where you can see the sky from any, you know, place on the earth any time of the year. But if we get some clear skies and if it gets dark enough, we should be able to see comet 12P Pons Brooks during the eclipse. So you ought to be able to see the corona, Jupiter, and right down here behind that cloud should be the planet Venus. So Jupiter, eclipse sun, Venus, and as a bonus, a double feature, we might be able to see the comet, you know, Pons Brooks. But I would say to you, don't waste a whole lot of time looking for Pons Brooks. You can see Pons Brooks, you know, day after tomorrow or 3 nights from now or even a month from now. Pons Brooks reaches its closest point to us in April, later in April. And so you'll have other opportunities to see that. But if you get a chance to see that and it looks like that, then that's cool. But don't spend too much time looking for that when you could be looking at the corona. Cause I love doing that. So one other picture, I took this just a few days ago with my C-Star S50 camera, telescope camera. So all of the sunspots that are here, really an active sun. Our sun is very close to its solar maximum. Interesting thing about the sun that I meant to tell you a while ago when we were looking at the magnetic lines of flux, each cycle of the 11 or so year solar minimum, solar maximum, solar minimum, at least once in every one of those 11-year cycles, the north and south poles, magnetic poles of the sun switch places. Now, can you imagine what that would do to Earth if our poles switched? But for some reason, scientists are still struggling with that, but the magnetic pole of our star switch places once every 11 years or so. And the magnetic lines of flux change dramatically in that switch. So I don't know how long we've been here, but I thought it'd be fun if we had a little review, a little bit of a test. So I want you to look at this image, see if you learned anything. Hope we never see that, right? So thank you for your attention. I would try to answer any questions you might have. Yes, sir.
So I saw that you had the picture with the magnetic lines. How did you take that? Was it just a long exposure?
I'm sorry, with what?
This picture with the photo lines, the magnetic.
Oh, yeah. It was just a long exposure. So when the eclipse happened, I had no reference. I didn't know what kind of ISO or what kind of shutter times to use. And so I just was banging away, change settings, bang away, change settings. And so I was just hammering away with 3 different cameras, trying to take a wide range. I threw away a third of my pictures. Easily a third of the pictures I just deleted because I didn't like the way they were framed, or I didn't like what I saw. But a couple of them to me were postcards, just amazing. And it was just absolutely photographer's dumb luck. So I won't claim any great skill because I was experimenting all the time. All during totality, I was shooting pictures with a camera that was connected to my 9¼ inch Celestron Schmidt-Cassegrain. I had a camera attached to my H alpha, and then I had a 300 millimeter telephoto lens on another Pentax camera that I was shooting through a solar filter. Just a look. Yes, sir.
For us, conversation precautions and use of the small glasses.
Sure. Yeah. From the time that you arrived, or the time the cloud rolled away, then you need your solar glasses on until totality. The trigger for that will be, you'll see, the very last thing you'll see is the diamond ring effect. And when it fades away and you have totality, and you can see, a ring of corona around the sun, then it's safe to take those off. The instant you begin to see the diamond ring effect on the other side, they need to go back on immediately. I meant to bring it, but my wife, I was going to throw it away. My wife wouldn't let me. But several years ago, I was setting up my telescope to do some solar imaging, and I have a first-class solar filter built by a company called Thousand Oaks, and it blocks 99.999 of the light. So I have an automatic telescope, excuse me, and so I was aligning the telescope, and so I knew I was going to go to the sun. It was in the daytime, all major targets as you can see. So I entered sun, pushed go to, and then I reached into my box to get my solar filter. Wrong order. Solar filter goes on first, then push enter. Because as I was trying to get the solar filter on the telescope, I began to smell something burning. And I mean, just like that, I burned a hole about 1/8 of an inch in diameter in my eyepiece cap. And you don't want that to happen to your eye. I mean, looking at the sun, particularly through some kind of an instrument, binoculars, certainly a telescope, is irrevocable and instantaneous retinal damage. So this is a beautiful thing to look at, but it's not worth your eyesight. So keep the glasses on until totality. Then you can take them off. Then you can look directly at the sun with no danger whatsoever, because the corona won't hurt your eyes, because the corona is going this way, because the moon blocks any photons that are coming your way. But the instant that the diamond ring starts on the other side, you need to look away, put your glasses on before you look back.
Right.
Yeah.
So I've been 2 years from the ISO,
The what?
ISO. Certificate.
Oh, yeah, if you have a pair of paper, frame, look on the earpiece probably, or maybe a little symbol right between your eyes that should say ISO. If it doesn't say ISO, throw them away and go to a good place. And by the way, if you have solar glasses that you had in 2017, they're not good for 2024. They last about 2 to 3 years, and then their filtering ability fades fairly dramatic. So if you have old ones, get rid of them and get some new ones. There are places everywhere that are giving them away like pancakes. So, get a fresh pair and wear them until totality starts. Okay, anybody else?
I've got a question from the internet.
Oh, sure.
Somebody wants to know, how does the total eclipse affect tides?
Tides.
Tides, yes.
So what affects our tides? The moon. So the sun is far enough away that it has no effect on our tide. The thing that changes our tide is whether the moon is at perigee or apogee. So if the moon is closer to us, the tides are higher. If the moon is farther away from us, the tides are lesser. But it has no effect. An eclipse is a combined, the combined in a line gravity between the sun and the moon and us would be negligible, as opposed to 10 days later or 15 days later. Yes, sir.
Simon Penning's photo composite of the International Space Station doesn't showed a great deal of texture on the sun. How did you do that?
Yeah, it's a hydrogen alpha camera, or a hydrogen alpha telescope that allows you to see the granulation on the surface of the sun. You can't see that in a normal white light. The images that you saw up here that were orange, that looked like the sun ought to look like, don't give you that detail. They'll give you sunspots, but that's really about all. And to see that granulation and the phase and the and the flares on the sun, you need to be looking through a H alpha telescope. And they're stinking high. They're bloody expensive. I should tell you how I got mine, but I'd have to swear you to secrecy. I was in a park named to be redacted. And this guy said, we've just bought a new Coronado telescope because the one we had is broken and we're throwing it away. And I said, throw it my way. I'll send it back to Meade and make them fix it. And so he said, well, it's in the dumpster out there if you want to go dig it out. I said, well, I ain't proud. So I climbed in the dumpster until I found it. And I dragged it out and it looked in the lens on each end, not cracked. Okay. So I set it up. Here's a safety pointer, pointed at the sun, held my hand over the eyepiece. Is it getting hot? Do I see a beam of light? No, I don't. So I carefully looked through it and I could see the sun, but it was horribly distorted. And so I focused it and it was perfect. So I went back to my supervisor with a box and I said, I fixed your telescope. And he said, well, the problem is we've already written it off the property inventory. And it is so difficult to reintroduce something